All right, so let's start off AP Physics 1, Unit 5, linear momentum, by just really talking about what is momentum, right? And so here are some great example pictures. So you see momentum in athletics with football and baseball. You also see it in cars and you can see the crash test picture, or crash test, the crash test picture there. So let's define what momentum is. It's a physics term that refers to a quantity of motion that an object has, right? So simply put, we simply call it inertia in motion. So what we're doing is we're moving a mass, okay? And so momentum is going to have two factors that it's going to rely on or depend on. The first is going to be the mass of the object, right? And so when you look at the phrase inertia in motion, right? Inertia goes to mass. And then the second one is going to be the speed, or more specifically, the velocity of the object. Because you'll learn later, we'll talk later here in a second, that it is a vector quantity. So we have to account for the direction, which means we're not really looking at the speed, we're looking at the velocity of the object. And so again, we go back to our simple definition of inertia in motion, right? Because the object is in motion, it's going to have a velocity. All right. Now, simple enough, the equation to determine. So one of the other definitions for momentum is the product of an object's mass and its velocity, right? And so that leads us right to the equation. So momentum is equal to mass times velocity. Okay, and it only took me a couple years ago, I've been in physics for almost 30 years, to figure out why it was the word, or the letter P. And that comes from this word, right? And that means to impede. And so if an object has momentum, it's going to impede, or if it's in a collision, it's impeding something. And so that's why they abbreviate it with P. I usually just tell students, well, there's already an M in the equation, so why would you have M equal MV, right? So was it going to be a capital M, a fancy looking M, the Greek letter mu? So, you know, it actually comes from the Latin word pater, to mean impede. But again, momentum is a vector, so that you're going to have to account for the direction because it's a velocity, and the mass is, and it's really going to be the vector component is going to be the scalar, or the vector piece, not the mass. Because remember, mass is always a scalar quantity. And this direction, this vector quantity, is going to be very important when we do conservation of momentum. Okay, because if I have two objects heading at each other before a collision, one of their velocities has to be negative because they're coming towards each other. Okay, or if I'm in an impulse momentum scenario, object's going to come in the positive direction, and then it's going to bounce off of a wall in the negative direction, which means the wall is providing a negative force to get it to turn around. So let's look at an example problem using this calculation. As you can see, it's a very simple calculation. All you have to do is mass times velocity. All right, so here we have determine the following momentum, right? So we have a 60 kilogram fullback moving eastward at 9 meters per second, a 1,000 kilogram car moving northward at 20 meters per second, and then you have a 40 kilogram freshman moving southward at 2 meters per second. All right, so all we have to do in each scenario, right, we're just going to do P equals M times V. And so scenario A, the momentum of the fullback is going to be 60 kilograms times 9 meters per second east, right, which we'll call the positive direction. We'll do our compass direction. So positive X will be east, positive Y will be north, right? South will be negative, west will be negative, okay? So all we do is 60 times 9, and it gives us a value of 540 kilograms times meters per second. Now, something to note is there's no special unit for momentum. It's just the unit of mass times the unit of velocity. All right, now we got the car going northward. So we have P is equal to 1,000, right? Because we have a 1,000 kilogram car, 20 meters per second northward. So our answer is going to be positive because we've already defined positive to be north. And that's going to be a value of 2 times 10 to the 4th. Again, kilograms times meters per second. And then finally, the freshman going southward. Okay, so we know that this one's going to be negative. And then we know it's going to be negative because we've defined positive to be north. And so we're going to have a 40 kilogram freshman times 2 meters per second. And we know it's going to be negative 80 kilograms times meters per second. So something that you see here, if you want to talk about the relationships, P is directly proportional to mass, which means if I keep everything the same speed or velocity, and I increase or decrease the mass, P will react accordingly, right? It's directly proportional. And then P is also directly proportional to velocity, right? So if I increase the velocity, I'm going to increase the momentum of the same object. Okay, so if I talk about that fullback, now he accelerates to 20 meters per second. What's his momentum now? So we know that we're going to just simply do 60 times 20. Okay, so now in the next video, we're going to start adjusting. We're going to start moving towards the impulse momentum theorem with talking about impulse.